for having me here today. So I will talk about something about planet formation, as Minka just said. So actually, for a long time, this field of planet formation has been dominated by theorists who came up with brilliant ideas and tried to understand how planets form in disks. And well, recently, with the advent of many wonderful telescopes like ALMA, we as observers can finally make some contribution to this field. So today I would like to share with you what we have learned about planet formation from the observational perspective. So to set the stage, let me start with this brief picture of what we know about star and planet formation. So usually we start in the interstellar medium when there is some overdensity in a cloud that suddenly collapses to form a young star in the center. And then a circumstellar disk can be formed naturally as to conserve angular momentum in the system. Initially, this disk was heavily embedded in some envelope structure. So those embedded phases, which refer to as class 0, class 1 disks. And then when those large envelope dissipates, we came to this planetary disk phase, where the young star in the center and the rotating disk around it can be directly observed. This is often called as class 2 disks. And planets was supposed to form out of this disk. So I know many of you in this audience are working on different steps along this track. I am particularly interested in those planetary disks, class 2 disks, and my talk will focus on this stage of evolution. If we're looking at the end product of this planet formation process, here I'm showing the known exoplanets in this video orbital distance and planet mass diagram. I think we should all be amazed by the power of nature in creating so many different kinds of worlds. Many of those systems are really unlike our own solar system. So there are close-in hot Jupiters and many super Earths, which are not in our system, but are quite common in the outside world. So a lot of progress have been made, even though the current detection of planet population can be largely incomplete as limited by those available detection methods. But a lot of progress have been made by using this large sample of detection and trying to trace back how they might form. While a lot of us would argue that one of the best or maybe the most direct way to understand how they form should be looking at their forming environments. And in particular, this huge diversity is very likely linked to the properties of their forming environments. So this is also one big thing in our disk studies. We're trying to understand how disk properties vary across different types of stars in around single and or binary systems, or even in different environments, and to see how those difference of disk properties can imprint on the resulting planetary systems. So broadly speaking, what do we know about disks? Here I'm showing an edge-on view of a cartoon of how a disk should be looking like, and as composed of gas and dust particles. Even though most of the mass resides in the gas, the solid content, as you all know, are essential for the makeup of planets. So as inherited from the ISM, those particles can grow to larger sizes. When they grow, they tend to settle towards the disk midplane, and that is the location where planet formation should proceed. And this stage of disk usually lasts for a few million years. And how do we know about that? If you can observe a system of young star system at multiple different wavelengths, you can come up with this spectral energy distribution. So for a young star with nova and temperature, we have its characteristic shape in this diagram. So they most emit at optical and near-infrared wavelengths, while we often see this long tail of emission towards far infrared and the millimeter, and those excess emission are from the disk contribution. So simply, if you can counting how many stars in a particular star forming region have those excess emission, then you know the fraction of stars still with disks. So we find that by reaching to about 10 million years, there's only a tiny fraction of stars still have remaining disk material. So that's how we know how long a disk can survive. Now, if you're looking at, again, SCD here, those bright emission at millimeter wavelengths also means that most of the disk area should be very cold. So to understand this, give you an idea of how this temperature distribution looks like. So for example, the water ice line is usually located within a few AU, while a disk can extend to tens of AU, like our solar system, or even hundreds of AU. So in that case, in that sense, most of the water in the disk are actually in ice form. So those tens of AU or maybe 100 AU disks, when they imprint, when place them in those nearby star-forming regions, they're actually very small in their angular scale on the sky. So usually sub-arcsecond scale. So which means that if we want to really resolve those disks, see what's happening inside those systems, we do need a very big telescope that operates at those long wavelengths. So all those disk properties really position ALMA as the best tool for disk studies. I know ASIAA is just a partner of ALMA, so I believe many of you know this facility very well. I just want to highlight two features of ALMA. So first of all, it can collect signal within tens of antennas simultaneously, which means that it can be quite sensitive to very faint disk emissions at millijansky level. In the meantime, the two antennas can be fed apart mostly by 16 kilometers, which means that we can really see details at AU scale of those disks. So this really makes, so this high sensitivity and high angle resolution really makes ALMA have made a lot of progress in the disk studies, and we have found many important implications of planet formation. I would like to first start with those medium resolution disk surveys that try to measure the bulk disk property like the disk mass and the size. Actually, such measurement can be done before ALMA, but they have been done in a very inefficient way. For example, in the torus survey, which was mostly done with SMA, and at that time, they would need like 1 hour observation for each target, at least 1 hour for each target, while ALMA can do that in a short minute. So which means that ALMA can really expand such study to a larger sample. Another thing related to those pre-ALMA observations is that this often associated with high upper limits. So the claimed correlation between the stellar mass and disk dust mass as viewed from the torus series was actually not that convincing at that point. But then when ALMA came, they opened this kind of demographic study to a number of nearby star-forming regions. Now this positive correlation between stellar mass and the disk mass can be robustly established. So it basically tells us that more massive stars tend to host more massive disks, which have a larger chance to form larger planets. This is actually consistent with exoplanet statistics, right? People find giant planets are more likely resides around those more early type stars. We can also look at these results in a different way. Here I'm showing the cumulative dust distribution for different regions of our survey, and also include those embedded disks as class 0 and class 1 sources. You see a clear decline trend of dust mass as disks move to more evolved stage. So some interesting claims have been made when we try to compare the dust mass in disks to the solid content in planetary systems. So earlier results by Manaro and Technic et al., they found that the available dust material in class 2 disks may not be enough to make up those observed exoplanets, while earlier class 0, class 1 disks do have sufficient mass. And recently, a work by Heiss-Muderer, they re-examined this comparison by taking into account the occurrence rate of exoplanets around different types of stars. And so now these two quantities can be more comparable, but still they are so comparable that, which means planet formation efficiency has to be very high, nearly around 100%. That's kind of too high. So a widely accepted explanation is that we would need to start planet formation very early on, well within 1 million years. So that's a basic idea. Actually, similar conclusions have been made for the formation of gas giants from the measurements of the gas disk mass. For example, we have did such analysis for Canadian-1 and disks. What we found is that based on the CO observations, those disks at 2 to 3 million years, they don't have sufficient gas to form even a Jupiter-mass planet. And so this also means that giant planets have to form early and much quickly than we previously thought. I have to admit that this is still area of active exploration because people are trying to understand which might be the best tracer to prove the total content of gas in disks. But I think the current direction is that class 2 disks couldn't be too massive. Of course, I think the most direct evidence of early planet formation really comes from the direct detection of young planets in disks. So here I'm showing the most convincing case we have so far. We have found 2 accreting giant planets in the inner cavity of P70, which is only about 5 million years old. And the 2 planets are well packed within 40 AU in the cavity. So here I'm showing the two planets and the associated disk from the UV optical to infrared and millimeter wavelengths. So basically different wavelengths try to trace different components or activity of those young planets. I think we are now quite convinced that at least some giant planets have to form very early. Now let's keep that timescale in mind. Let me give you a brief picture of what we know about how to form a planet from the classical picture, this co-accretion model. So you can imagine as to form a planet, those dust particles from the ISM need to grow their sizes by at least more than 12 order of magnitude, which is huge, which means it's not a very easy task. So due to this vast range of size increase, so we tend to split the process into multiple steps. And the key part is to make those cores that can then accurate gas to form the planet atmosphere. While informing the core really relies on those intermediate sized objects, those planetesimals being abundant in the disk. And those planetesimals are themselves formed by those millimeter, centimeter sized pebbles. So from laboratory experiments, we know that small ISM dust can easily coagulate to form pebbles. While in the disk environment, those pebbles, before reaching to planetesimal size, they will encounter a number of theoretical barriers. So here I'm listing a few, and I think one prominent one is called those radial drift effect. So what is radial drift? So radial drift refers to the pebbles in a gaseous disk, so which always tends to move towards the region of high pressure, which is usually the location close to the star because both temperature and density are high around the star. And this radial drift process is due to the fact that for gas in the disk, which can feel the pressure force, which always operate outwards, so while the pebbles won't feel the gas pressure. So pebbles will move freely in the Caparian speed, while the gas will move slightly slower than that speed because of the pressure gradient. In that sense, the pebbles will encounter headwind from the slowly moving gas, and then they lose angular momentum and then move inward. So you can imagine there's a difference of how pebbles would distribute compared to the gas. We have found some evidence from observations for this radial drift process. So for example, in our recent study, we tried to compare the gas distribution with the solid distribution in a large sample of disks. And for the gas disk, we're using the CO emission to trace it. So here I'm showing the gas CO emission in the magenta line here, and which is usually a factor of few, like at least 2 to 3 times more extended for the gas disk than the millimeter solid distribution. So if the difference is only a factor of 2 to 3, which can indeed be explained by the opacity difference of the two tracers, because CO emission is often optically thick, and we can easily detect it even though density is low in the outer part. While for millimeter grains, their emission are most likely to be optically thin, and opacity drops quickly in outer parts. So there's a natural difference of their distribution. While in some cases, we found that the difference of the two species can be a factor of 4 or even 7 in the most extreme case. And in those cases, the opacity difference couldn't really explain that observational difference of their distribution. So those disks provide the most clear evidence of radial drift really happening in disks. Well, there's a problem with radial drift. It is that it can happen too quickly. So we can run out of particles in the larger grains in the outer disk in a few million years. So that is actually the time scale of the disks in our consideration. So that means that we don't have those pebbles, those larger grains to form planets, which is bad, right? So how can we reconcile this? Actually, the solution was proposed when this problem will be found. So we can imagine that somehow we can build pressure bumps in the disk. So instead, grains, instead of moving towards the central pressure peak, they can be trapped in those local pressure bumps. So they can be sustained at large radii because they're trapped there. So in principle, we would expect that a large disk at millimeter wavelengths, they should show disk features like those radially varying profile. Well, for a long time, this was not possible because we don't have that good resolution to really tell if that's the case or not. So this is the disk of HO tau, as you can see, pre-ALMA at a resolution of 20 AU. We couldn't really tell if there is robust features in the system. While soon with ALMA, people all know this figure, right? So the HO tau disk, there's no doubt it shows multiple sets of gaps and rings, and those features we often call as substructures, and they can be only reviewed at ALMA's resolution. Later on, ALMA has found more and more disks with substructures, and here I'm only showing a small collection of them, but they are selected from different star-forming regions, so the basically choice means that those features can be widely present at different evolution stages. And even more recently, we have found such features in those embedded earlier phases. And I believe we will find more and more from those kind of analysis. And so I think all those results is really converging to a point that substructures might be very common in disks. And they might even represent as a fundamental piece of the planet formation process. However, I have to mention that all those observations, most of them are tend to, by design, to target those bright and large disks. So in order to establish a more empirical understanding, a complete understanding of those substructure emergence and properties, we would need a more representative sample. So that's why I'd like to spend more time on our survey of torus, which we have used a different design strategy, and that showing might have you different insights from those observations. And I will give you some overall key features of those substructures as viewed from our survey. So as we are trying to provide a more generic view of substructure emergence, our main selection criteria in this survey is trying to just pick up stars with spectral type earlier than M3. As you know, there is a correlation between stellar mass and disk luminosity, disk mass. So which means that our selection can also be biased towards, slightly biased toward those brighter disks. But as you can see here, I highlight our 32 disks in this stellar mass disk luminosity diagram. They kind of sample a wide range of disk brightness. So I guess they present a more, they show us a more representative sample of disks around solar type stars. So we have choose an intermediate high resolution 0.1 second, which allow us to map the dust distribution in disks at 10 AU-ish scale. Here I'm going to show you how they look like at 1.3 millimeter image. I intend to order them by their millimeter brightness, so you can see that those brighter ones on the top and the fainter ones in the bottom. So we have found the 12 disks with visible substructures, and they indeed have been found both in bright targets and also in fainter ones. In the meantime, there are also many other disks which looks quite featureless by eye, but they can be as bright as those disks with substructures, so which I will talk about later. But let's try to focus on those disks with visible substructures. So from our blind search, we found that the most common type of substructure detection should be those asymmetric gaps and rings. We do find in some cases there is subtle azimuthal asymmetry, but those features are quite rare. And at least with our sample, those high contrast azimuthal asymmetry and even spiral patterns should be even rare based on our search. And those features have been found in all types of stars covered in our sample, so from A-type stars to M3 stars. Then, in order to better characterize and quantify those properties, we built 1D parametric models using combination of different functions, for example, like Gaussian rings, Gaussian profile, and tapered power law, and to fit in the UV plane and to reconstruct the intensity profile. So you can see that those gaps and rings have been found in all disk radii. They can be found down to the resolution limit and also out to 100 AU. But I think the most important bit is that they do show a wide range of diversity of their properties. For example, the number of substructures that each disk can host can be very different, and in their locations, weights and depths, everything can be different. So here I summarized the key features of substructures from our survey, but I think a few key points really can still hold even if you include other observations together. The only difference might be substructure detection can be even found in late M dwarfs, like M5 stars, and they have been found in even closer radii that is beyond our resolution limit. So within those 32 disks, we also have 20 targets that we have tried to fit using a tapered power law function, and which can roughly match with what we find in observations. So we couldn't robustly establish whether those targets do host substructure or not. So here in the right-hand side, I'm trying to compare the size of those disks in those ring detections and with those, I call them smooth disks. And I also further divide the smooth disk sample by around the single stars or binary systems. So apparently you can see that those smooth disks looks much compact than ring disks. And those disks in binary systems are even more compact. So we can actually apply our previous mentioned video drift picture to this observation finding. So I think the picture we're finding here is that for those substructure disks, they are large because somehow they can build pressure bump early on in the disk. So they can sustain larger grains at large radii, so they keep as big and showing features. While those smaller disks, they may have just loosed their outer disk through efficient radial drift. And recently, theoretical studies have even found that in binary systems, because of tidal truncation, they can actually accelerate the radial drift process. That's why we see an even compact distribution of dust in those binary systems. So I think this radial drift scenario really explains why we don't have substructure in the outer part of those small disks. I think another question you might wonder is that would radial drift be so efficient that we also need pressure bump to sustain the current small disks? I think I do want to elaborate this idea based on this extreme example of geotau. So recently we found that geotau indeed has two rings in outer parts which go beyond 100 AU, while at the meantime its CO disk can extend to 1000 AU, which is huge. So we're wondering how dust evolution might be look like in such a huge gas disk. What we found is that even without substructure, without those pressure bumps, the dust disk can also go beyond 100 AU. This is because in such a large disk, the green growth and radial drift do take a quite longer time. And then your grains will just drift toward this point of 100 AU. So in analog, I think we can apply this idea to our small disks. If those small disks, they do host a large gas disk, pressure bump will not necessarily needed from a theoretical point of view. Well, recently we have re-examined those small disks by using a different fitting framework by directly fitting towards the visibility of those oscillation components. So what we found is that in a few cases, we indeed find hint of substructures. So here I'm showing 3 examples, and on the white column showing the modeled intensity profile. So mostly the features are quite shallow, so it's really hard to tell from our previous observations, from our previous modeling, and even by looking at the image. Well, I have to admit that this way of fitting identified substructure can be largely incomplete because of the large beam size compared with the small radius of the disks. And recently, we have obtained high resolution observation, like 3 to 5A resolution for 2 disks. So indeed, we are finding some difference. For example, in BP tau, the super resolution modeling tend to find inner cavity there, while in reality, it hosts a very bright inner component inside those deep gap. And in the case of DQ tau, those modeling couldn't even recover those shallow features in disks. So I think in that regard, high resolution observation, like what ALMA can provide in the longest baseline, is really needed for us to correctly interpret those features in small disks. Now, even though we only have a very small sample, I do believe that substructure might be as prevalent in small disks as those in larger disks around solar type stars. Now I'd like to jump out of our torus sample and look at the overall disk substructure detections. So here in this diagram, I'm trying to highlight those disks with substructure, those disks with high resolution observation available as colored dots. And then those gray points are showing the bulk disk population as comparison. So indeed that many of those disks, when they observed at high resolution, they do show substructures. Well, you might notice a immediate problem here is that most observations are heavily biased towards those white disks around solar type stars. I want to emphasize that we are currently have no idea what disks looking like around AM dwarfs. Indeed, AM dwarfs actually important planet hosts. For example, if you're looking at the planet statistics, here I'm showing only one example. So those orange dots showing the distribution of gas giants, and the small green dots showing distribution of planets, small planets with size smaller than Jupiter. So actually around AM dwarfs, small planets are even more common. So they might also imprint features in those small disks, in those AM dwarf disks. So we're very interested to understand how the planet formation condition might be different in AM dwarfs around compared to those solar counterparts. But as you can see that those AM dwarf disks are usually much fainter than those solar counterparts. So they are typically smaller in sizes. So, and then probing them becomes even more challenging. Actually, we have conducted some earlier work by targeting those brighter disks in torus of AM dwarf targets. And indeed, we found that the 3 brightest ones do show substructure. But as you can see, the main population of M dwarf disks are still not sufficiently explored so far. And in that regard, we have carried out another survey and trying to probe this empty parameter space. So we have here, I'm only showing some initial results from our survey. We have proposed with ALMA to observe 16 targets, but only 6 have been observed. But even with 6, I think we have some promising results to discuss. So in 4 of them, we do find substructures, and the remaining 2 are so compact, they are barely resolved at 5AU resolution. An interesting part is that here, all 4 of them do show deficit of emission in the inner cavity. So you can see the inner cavity there. So actually, only looking at this small sample, we found that the occurrence rate of inner cavity might be higher than around those disks around the solar type stars. I think this is I'm not sure if this is a really coincidence of our random selection of ALMA to do observation, or it really reveals some important differences of evolution in disks around different types of stars. I think it's an interesting question that we would like to explore further. So a grad student that I'm co-advising, Yang Fanshi from Peking University, is actually working on the sample analysis. So stay tuned if you're interested in these results. So now we have talked about that we have nerd substructure might be quite common in disks around different types of stars. The next question we should ask is, okay, what might be causing them? And so here, this figure is a very complicated summary of those many proposed scenarios that can create substructures. I just want to emphasize that besides the dynamic interaction with companions, there are many natural disk physical processes that may associate with fluid instability and that may or may not involve magnetic field can really do the same job. Well, among all those mechanisms, I think ice-line is the one that we can really easily test, as their location can be easily predicted if we know the disk temperature structure. Actually, the physical hypothesis, what happens across the ice lines, I think is still highly debated. And the general idea is that when pebbles across the ice line, they sublimate, and the dust emissivity can really change inside and outside the snow line, so they appear as bright and dark emission. But it's unclear how the physics really happen in there, because the feature there can be enhanced emission inside the snow line or outside the snow line. But in any case, from observational side, we can really test if the location of those gap and rings match with the location of expected ice-line location. So do they show a strong spatial correlation? That's the thing we really want to test. So back in 2018, in our paper, we tried to do this initial analysis. Indeed, we found that in this case of CI tau, for example, there are 2 gaps which have same location with the expected ice-line location. So that's quite good. But there are still many other cases which don't match. And by looking at an even larger sample, mostly we found that those gap and ring location do not show strong correlation with the stellar luminosity, which is a proxy of this temperature. So that means ice-line couldn't be a universal mechanism. So there must be other processes get involved. Actually, ice-line is not able to make a pressure bumps. They couldn't really trap grains there. But many other scenarios, as listed in the summary figure, they do produce pressure bumps and then they trap grains. For example, in the case of planet interaction, a pressure maximum can be built outside the planet orbit. So around this pressure maximum, grains of all sizes can accumulate there, but larger grains will be more pronounced in their accumulation, which means that those larger grains will be radially confined in that location. So translating this into observations, we would expect that at longer wavelengths, which tracing larger grains in those dust ring location, they should be more narrower. Recently, we have tried to conduct such analysis in a few examples, and we only find in one case a very marginal evidence of this dust trapping might be happening. I think one reason could be that the ring is not well resolved at our 10 AU resolution. But another side is that we might need to move to longer wavelengths where this effect would be more pronounced. Actually, we have got some very decent data of VOA data, which indeed have found a dust ring in the outer part of a disk. So hopefully next time I can talk to you more about that part of the result. Of course, about the pressure bump scenario, I guess many of us are very excited about the idea that young planets may just hide in those dark, empty regions. Actually, we are currently very good at making planet interaction models to expand those observations. So here I'm showing one example of HLTAL. On the left-hand side is observation, on the right-hand side, only one of many attempts trying to expand those observations. So I think they match quite well. And so based on those excellent match, we can actually using those models to estimate where those planets should be and how massive they are in those disks, and that help us to come up with a constraint on those young planet population. So this diagram gives us what we know about this young planet population based on ALMA disk observations, showing as those color symbols. So very interesting. They are mostly low mass planets in wide orbits and filling up those empty parameter space, which are left out by other planet detection methods. So I think this is really making ALMA a planet search facility in the last few years, which is very exciting. Now I do want to try to draw attention to the four red symbols on this diagram. So they are the four, I think they are the more like most convincing case we have for young planets. Of course, the first two are the most convincing ones. The twos are the two planets in the P70 disk that I have introduced in the beginning. Another candidate comes within the inner cavity of AB Auriga. So here the red emission shows the ALMA millimeter image, and the young planet candidate was indicated by the green arrow. Even though this claimed detection have been found in multiple telescopes and multiple epochs, and their detection of H alpha is still quite debated. So recently we have did analysis using HST observation. We found that it's really hard to disentangle that whether that H alpha emission is tracing accretion of planets or they are just reflecting the stellar light. So I think there's still a debate and a lot of progress have been made on that regard. Another case is what we found in the outer part of AS209. This is actually made with ALMAs. What we found is that there is like a point-like source emission of certain CO in the outer disk that only showing up in a few velocity channels, and they are exactly resized in a CO gap in the disk. So we propose that this might be tracing the gaseous disk around a giant planet, so they're tracing a gaseous CPD disk, which is quite nice. So the four systems, actually, if you look back to the plot I showed at the beginning, they are actually a few Jupiter mass, so they are residing in the top part of the young planet population. So I would say that we are currently quite unsuccessful in a direct search of young planet. While given the current upper limit of a few Jupiter mass, I would think this non-detection is not that surprising if our inference of the planet mass based on those disk features are indeed correct. Well, I do have to admit that those measurements of planet mass actually associated with large uncertainties and mostly related to our ignorance of those many fundamental disk properties. For example, viscosity, we don't really know what's happening with viscosity in disks. So you can imagine in a low viscous disk, even a single planet can open multiple gaps, which means that we should be cautious in directly relating one gap to one planet. Actually, I do want to emphasize this idea a bit more here. So I'm showing two examples of HO tau and AS209, and both shows multiple sets of gaps and rings. Now people try to tend to expand them with pan-disk interaction models. Here I'm showing the models, which looks quite good compared to the observations. Well, in the case of HO tau, we have used a few multiple planets to expand the features. While in AS209, only one planet is input in this wide cavity with a slight tuning on the viscosity distribution in the disk, alpha distribution in the disk. So I think this is just a hint to tell us that, okay, we should be cautious. Either if we want to really associate with what we observe with ALMA to young planets, we should either find in that point source, or these have to be combined with many other dynamical evidences. Now, if we look closely to those interaction models, the planet actually pushed away material from its orbit, so which forms the so is often seen gaps in those ALMA images. While in the meantime, it can also drag some material moving with it, form those co-moving horseshoe orbit. So here in this example of the gas distribution, you see that many gas materials resides in this gap. And on the right-hand side, I'm showing the millimeter grain distribution by using different planet and disk properties. So when this condition allows, those material can be preferentially accumulated around those Lagrangian points of the planet star system. So they have some characteristic feature because they should be separated by roughly 120 degrees. This is actually very similar to the idea if looking at our solar system, we have those Trojan asteroids that are moving along with Jupiter. So they will those asteroids were trapped in those Lagrangian points, and they are separated 120 degrees. And recently we have found such evidence in one disk. I think it's very interesting. So this is in the disk of Nicasium 15. If you have been in the field for a while, you know this is a very famous system because this is the first disk where penta candidates have been proposed back to 10 years ago. And then people have later found H-alpha emission associated with those previous claimed protoplanets. But very recently, people tend to argue that those previous identified protoplanets may just be tracing some of the inner disk emissions. So there's a lot of debate happening in those systems. So we are trying to look at this and trying to contribute to this controversy from the millimeter perspective. So ALMA, this disk is so famous that has been extensively observed by ALMA. It has many hours of long-based observation in the archive. So we have combined all that together and obtained a very deep and high-resolution image of Nicasium 15. As you can see now, this single ring in those old image have been resolved into multiple rings. And in particular, we find a very faint ring within 42 AU in the disk. And this faint ring is quite visible, and it's much fainter than the outer two rings if you're looking at the radio profile here. Now we can zoom into this radio profile. Here I'm showing the ring intensity profile along the azimuthal direction. So you can see how the emission varies along the ring. We found that this ring is actually not homogeneous. It exhibits two prominent axis emission features, one as unresolved clump and one as an spatially elongated arc. And those two features are brighter than the ring baseline by at least factor of 2. And more importantly, they are separated by 120 degrees, which is quite interesting. So we have tried to better characterize the two features by looking at their residual map. So we built up an axiometric azimuthal-symmetric model and subtract that in the UV plane and to reconstruct how the residual image should be looking like. We have done this separately into ALMA bands so we can check the consistency of the detection and also to see if there might be any spatial offset of those features. So what we found is, okay, those detections are quite robust. They have been detected in both bands. But if you're looking at their comparison, there's some interesting feature. So the clump is actually show some offset. So usually when you see a clump, a point-like source in the disk cavity, you might wonder, would that be a circumplanetary disk that's tracing the young planet? Well, the offset really means that it couldn't be a CPD, because for a CPD, we would expect it to be stationary at different bands. Well, instead, those morphology, I think the similarity of morphology between observations and also expected from those models really telling us this ring might be tracing the planet Horseshoe ring at 42 AU. And in this case, we can really pinpoint where the planet should be, which should resides in the two longing point that's trapping in the middle of that part. The way this is quite promising is that we can really search for signals around this planet and understand the properties around those planets. Actually, such analysis has been. I should also mention that this picture has been supported by the multi-wavelength analysis in our paper. That if you're looking at the image at the two bands, the band 6 image is much sharper, which means that have higher contrast, and the ring outside the planet actually are much narrower in the longer wavelengths, which is consistent with picture we post that there's a pressure bump outside the planet orbit. I just mentioned that actually, if you know where the planet should be, then you can trace the morphology and then the surrounding of that planet. This is how people find the CPD around P70C. Unfortunately, we haven't really found any signal around our Licasium 15 disk, Licasium 15b planet. If we try to place the upper limit we obtained, compare them with those detection from the circumplanetary disks, we really found that we are really close to their detection limit, but there's just nothing appears. So in this diagram, the gray dots are showing the luminosity of disks around stars. They tend to kind of fall in line with those CPD detection around planetary mass objects. If this relation really hold, I think we still have a long way to go in order to search for CPDs around the planets reviewed from ALMA disk features. So I think I've talked a lot about those substructure emergence in the last few minutes. I want to quickly briefly discuss what does it mean for the wide presence of substructures for planet formation and for disk evolution. So one part, no longer what is causing those features, those high density rings have been proposed to be important sites for planet formation because of a high density. So we can actually assess this condition by looking at the green properties there. Here I'm trying to address with two examples. What we found is that the spectral index calculated from two different wavelengths, they tend to reach a local minima around this high density ring, which means that there might be presence of larger grains in the ring compared to other regions that put those dust rings as optimal condition to forming young planets. And in the meantime, people tend to characterize those features of substructure. What they found is that if you include planetesimal formation, it can well explain observed opacity in those dust rings. And if not, and those rings will have much higher optical depths. And so the idea is that if we couldn't efficiently remove pebbles in those dust rings, we should expect a much higher optical depth. That points to the idea that we should expect planetesimal formation in the rings. On the other hand, since the presence of substructure really regulates the dust evolution in disks, so this might have a profound implication for disk chemistry. So recently in a paper led by Andrea Bandati, we found that the water content traced by Spitzer spectrum was actually much higher in those inner region of small disks, which the idea we found is that maybe those small disks are indeed resulted from radial drift. So when those pebbles go across the water flow line, they can sublimate and enrich the inner disk water content. while opposite will happen for larger disks because basically just don't have those pebbles were trapped outside. They are disconnected to the inner part. So I think we're going to test this idea better with the combined effort of ALMA and James Webb in the coming year. So from ALMA side, we were going to prove this dust distribution in more detail. And with James Webb, we're going to measure the optically thin waterline that can better prove the total content in those disks. So I think I want to make a brief summary here, what we have learned about planet formation from ALMA. So basically, we have learned that from the mass budget and also importantly from the detection of young planets, planets should be formed quickly. And we have found a lot of substructures in disks that are quite common across different types of stars. And there must be some universal mechanism to cause them. They are either caused by some fluid instabilities, or they are imprints of young embedded planets. And at the meantime, those substructures can be the important sites for the formation of next generation of planet. I do want to connect back to the picture that we proposed at the beginning. So here is actually my reversed picture of how those calculation planet formation should be work. So planet formation really starts early on. And so at the embedded disk phase, those fluid instabilities can really produce pressure bumps. And within those pressure bumps, we can quickly build planetesimal planets. So we move into the +2 stage, we're actually looking at those well-assembled planets. So we can search for young planets directly. While in the meantime, those substructures in +2 disks can form new planets. So there might be a sequence of planet formation really happens in disks. So that being said, I think the key of planet formation really resides in the earlier stage of embedded phases. And I'm really looking forward to the EDIS large program, see what they might find there. So I think I will stop here and happy to take any questions you might have.
Thank you, Feng, for the great talk. You can use these applause emoji to give Feng an applause. Question time. We have plenty of time for questions. Let me look at I saw a hand raised somewhere. Was it Tang Tang? You can just speak up.
Hi, this is Yawen Tang, a very nice talk. So I have, and you have shown a lot of nice results from the large program, also a very rich ALMA data. So I have a question about your demographics of the survey with the you found 4 disks with, you resolved that with 15 AU resolution, where you found 2 of them or 3 of them with a cavity at the middle. I'm wondering, in this kind of resolution, usually we are reaching to the opacity, very high opacity in both gas as well. So have you checked if when you remove the contribution from the gas component, how do you get around with the possible optically thickness toward the center of the peak? So therefore, this cavity you see toward the center might be biased from you are removing too much gas, in which you mimic a hole in continuum.
Yeah, that's a very good point. Actually, we do have 3 observations of the targets, at least in this, but these are quite shallow observations, so we don't really have a full picture of how CO might be distributed in the system. But at least in one cases here, we do find there is deficit of emission of gas in the inner part. So I think in this case, we do find a cavity of gas, so they couldn't contribute too much to the opacity by subtracting for the dust. Yeah, but I'm not sure for the other cases how that might be possible. Yeah.
But you can check that with the gas CO emission. You check the brightness temperature. If it's about the same level as your dust continuum, you extrapolate from the outer part, which you think it should be optically thin in molecular line. Then you can estimate how much is the bias from gas component, right?
Yeah, but if we are looking at a different wavelength window outside of the CO emissions, I was wondering how that contribution might be there.
You're talking about the different radius, or you're talking about different wavelengths? It's different
Wavelengths. So this is continuum emission, but they are not at the same wavelengths of the CO emission. So they are not really, CO couldn't really contribute to what we see at these wavelengths of dust.
I see. So in your observation, you avoid all these
yeah, we do include CO, but they are, when we're doing the continuum map, we exclude the line emission regions.
Okay, I see. Thank you.
Okay, Nagayoshi, please go ahead.
Thank you. That's very interesting talk. So I'm interested in your small disks, which is not showing any substructures. So according to your explanation, you said those small disks may had a larger scale, and then somehow outside of the disk just gone, and then because of a radial drift of the dust, this becomes smaller. That would be very interesting way to explain. But I was also wondering whether those disks might be intrinsically small. That's why you don't just see that any structure because it's too small. So is there such a possibility?
Yeah, actually, I didn't mention that we do propose that scenario. That's why we have some CO observations for this target. So we are trying to assess by looking at the CO distribution, is that really forms small or it has a large CO disk? Yeah, I think that's a very good point, because we know that from this formation scenario, you can build either a large one or smaller one, depending on how the magnetic field can orientate in the disk. Yeah. So we do have data for those targets. I haven't really checked them. So I will let you know when I finally got the results there. Yeah.
Okay, that'll be great. Okay, thank you.
We have a question from Jinshi. Yeah, please go ahead.
Yeah, thank you very much for interesting talk. Yeah, it was very interesting. So I have a question about the origin of substructures in disks. So you mentioned that if there is a pressure bump, then the ring should be sharp. But is there any expectation like how sharp it should be? I'm wondering if what parameter can be good indicator to distinguish different origin of substructures.
Yeah, I think that's quite challenging because many of those processes I listed here, they do produce substructures, but they maybe have different levels. Especially many of those fluid instabilities, they're creating multiple series of substructure and at very small scale, which is around like scale height of the disk location. So actually to observationally resolve them is one big challenge, because you can imagine if they are scale height only 1% or 0.1, and then at 10 AU you need like 1 AU resolution to really do the work, which is quite challenging. But I think planet might doing some difference, because we are expecting at least for some dead zone scenario and our planet scenario, the distribution of different population of grains can be different. They have their peak can shift a little bit. But I mean, for the sharpness of the edge, I think that's a quantity really hard to constrain from observations, because you always convolve with a Gaussian beam. Really hard to tell how the shape of the pressure bump would be there. Yeah.
Okay, thank you very much.
Okay, any other questions? If not, I will squeeze one last one myself. So my question is, I'm not an observer, obviously, but you may be aware that the institute here is involved in ALMA Band 1. So I was wondering if that is useful for what you're looking at, the inner disk, because for Band 1, I guess you can look at like large grains, right? Maybe up to centimeter size grains. So do you have that? Are you interested in using it, or was that useful? Just want to get a comment from you.
Yeah, so I think it's helpful to really go to the larger grain population, but still we should remember that Band 1, because it's longer wavelengths, was still limited by resolution. So we have a poor resolution compared to what we can get at the normal band 6, band 7 observation. So even so, for in those inner disk, they might be optically thin, but we are still don't know how the exact distribution of those particles.
I see.
Yeah. So
we
I
have
think
one
that's
question from
one
Qingfei.
challenge.
Okay. Okay, thank you. Qingfei, please go ahead.
Nice. I thought I can use a last minute question. Hey, thank you for the nice talk. I wondered, this radio drift is very important. I mean, the fundamental process, right? So is there any way to confirm that directly? I mean, how to confirm that radio drift motion?
Yeah, we did that by just looking at the distribution of gas and solids, right? So if we see a big difference of their radial distribution, in some cases they are very extreme. So I think those are the cases where radio drift really happened. But if the difference is quite marginal, only a factor of 2 to 3, it's hard to tell because opacity can make that difference. And in those systems, actually, most of them have pressure bumps being built. So radio drift, the effect was actually removed by the presence of pressure bumps built early on. Yeah, but I think those example of extended gas disk compared to small dust is really telling us that there must be radio drift happened. Otherwise, I don't know if there's any other explanation can explain that.
Okay. Yeah, I'm wondering whether there's some direct observation that can prove that directly instead of comparing this gas and dust stuff. I know there's kind of outcome of this radio drift, but I think it's something more direct.
Yeah, people also claim that for the dust particle, they should have a sharp outer edge. So that is also one scenario we should expecting. People have claimed that, but I don't know if that's a real thing here because we also did that in our modeling. We are trying to using a tapered power law to fit data, which looks good, and then we claim this might be radio drift happening. But then later on, we found okay, that function is not a good way to model our data, so it's unclear. Yeah.
Okay, thank you.
Okay, thank you, Qingfei, for the question. We're out of time, so let's thank Feng again for the great talk. Please use the applause emoji. And with that, I will close the session. Thank you again.
Thank you all for joining. Yeah, bye-bye.
Thank you.